Hello, this is my video for explaining take-home test 1. So looking over the problem, first I'm going to split it up into two parts. Part 1 is before the switch, and we've actually seen this circuit in discussion 1.2, which is an instrumentation op-amp, which has two inputs and also goes through a difference amplifier. And so first we are going to look for an expression for V1 and V2 that relates VI1 and VI2. So we look at the op-amp rules, which are IN equals IP equals 0. And since there's negative feedback for all three op-amps, we know that VP equals VN. So now we're going to first find an expression for I, the current, which I've drawn here on the circuit, and we know it follows this path again because of the op-amp rules listed here. And so we get I equals VI2 minus VI1 divided by 2K, which is this resistor here. And we know this is VI2 and this is VI1 because the voltages between the inverting and non-inverting terminals of the op-amps should be around the same as written here. And so now we use KVL and voltage rules to write an expression for V1, which equals VI1 minus the voltage drop over this resistor, which is 1K times I. And then for V2, we have this path here, which is V2 equals 1K times I plus VI2. And so from there, we can plug in our expression for I into V1 and V2 so that we can get two equations that only have VI1 and VI2 with the no current variable in there. And for the second part here, which is the difference amplifier, we can see that the two inputs into it are equal to what we just found, which are V1 and V2. And from class, we know that the equation for the difference amplifier is V out equals RF over R1 times V2 minus V1. And so now we just use this equation and plug in V1 and V2 into it, as well as the resistor values from the circuit. And we can simplify all of this down until we get 2 times VI2 minus VI1. So now we have three equations for each, so V1, V2, and V3, and these are all in terms of VI2 and VI1. So now we want to sketch the graphs for each of these voltage points, and we can do this by looking at VI2 and VI1, which from the beginning we know are these two square wave functions that are opposite of each other. And so we can plug those in and look at just a single period and split it up from 0 seconds and 0.5 to 1 milliseconds because that's when it switches in voltage values. And so here we can plug these values into the equations that we found, and what we get is V1 and V2 are square waves with maximum values of 2 volts and negative 2 volts and are opposite of each other. And V3 is another square wave that goes from negative 4 volts to 4 volts. And all of these have the same frequency as the input signal because we were just adding signals together. There's no change in their frequency. So for the next part, which is after the switch, since now we have the final signal for V3 here, we know that this switch closes at t equals 1 millisecond and then goes into this part of the circuit, which is an integrator amplifier, which we've also seen in class. And so here is the graph for V4, which is after the switch. And since the switch is open from t between 0 and 1 milliseconds, we know that the voltage at V4 is 0 during that period, And then once the switch is closed after 1 millisecond, the same signal from V3 starts going through. And so this is why we see something that looks like V4, but it starts at 1 millisecond. So that's the signal for V4. And so now we are looking at the integrator amplifier with a DC gain control because of this resistor. And we can, we notice the configuration of the capacitor and resistor, so that's how I know it's an integrator. And from 0 to 1 millisecond for V out, we know that it's equal to 0 because V4 during this first millisecond is equal to 0, and the voltage across the capacitor is 0 before the switch closes, which was mentioned in the problem. So now we just have to look at after t equals 1 millisecond and the switch is closed, what the graph will look like. And so in order to solve for this, we first need to find out what the RC time constant is, which we take from 10 kiloohms here and 10 nanofarads and multiply them together, and we get 0.1 milliseconds as the RC time constant. And then from class, we found this equation right here, which is the ideal voltage output for an op-amp integrator. If we plug in values for this using the V4 graph, we can see the maximum will be 4 volts for half a period and then negative 4 volts for the other half of a period. We plug that in and we get a slope of either negative 20k times t or 20k times t, depending on if you're on a negative or positive voltage value. To get more specific into the time domain analysis, if we look at from 1 millisecond to 1.5 milliseconds, Vi is 4 volts. We can plug that in into this V out equation and we will get negative 40k times t, but there is a constant that is added to it at this to try and find the slope. So to solve for that, at 1 millisecond is equal to 0. So at 0, we plug in this value, the slope, and the time to find this constant value here. And then at 1.5 milliseconds, we plug it into this equation we found, and we know that the V out at 1.5 milliseconds is negative 10, or sorry, at V out would be negative 20 volts. However, negative 20 volts is larger than our V saturation for the op amp, which is negative 10 volts, which means the slope will be negative 40 kT, but it will the voltage will stop at negative 10 volts because the op amp is saturated, which we'll see in the sketch later. So using this value, we look at the second half of the period where Vi equals negative 4 volts, plug it in, we can see the same slope again, find the time constant, plug in the 2 millisecond value at the end of that portion, and then we get 10 volts. And we continue doing this for the other half period values. And so using these points, we can see that from 0 to 1 millisecond, it's 0 volts. Then we have this steep slope. However, right here, the op amp gets saturated, which means it stops at 10 volts. And then from this point, we switch and we see a positive slope here because we have a negative input voltage. And then this keeps going back and forth between negative and 10 volts. And we see this kind of triangle wave here at the end. Thank you.